Hey guys, welcome back to the channel. Today we are diving into Heap Sort, a highly efficient sorting algorithm that uses a binary heap data structure. Let's start a quick summary of how Heap Sort works before jumping into the animation. Heap Sort is a comparison-based sorting algorithm that uses a binary heap data structure, which is complete binary tree. It starts by building a max heap from the input data, where the largest element is at the root. The largest element is then repeatedly swapped with the last unsorted element and removed from the heap. After each swap, the heap is restructured, or we call it heapified, to restore the max heap property, ensuring the largest element is always at the root. This process continues until the entire array is sorted in ascending order. Heap sort has a time complexity of n log n in both worst and average cases, making it a reliable choice for sorting large datasets. Now let's dive into the animation to visually explore how heap sort works in action. We start with this unsorted array of numbers 6, 5, 3, 1, 8, 7, 2, 4. Now we'll begin building a max heap for these numbers. First, let's understand what is a max heap. A max heap is a binary tree where the largest element is always at the root and every parent node is greater than or equal to its child node. This property ensures that the root is the max element in the tree. So on the screen, 8 is greater than 5, which violates the max heap property. So we swap them. Since 8 is also greater than the root, that is 6, we swap again to restore the heap. This process of adjusting the tree to maintain the heap property is called heapifying. Heapifying is crucial because it ensures the max heap property is maintained after each change. Without it, the structure wouldn't guarantee the largest element at the root. This lets us repeatedly extract the maximum and build a sorted array efficiently. Once the heap is complete, we start moving back the numbers back into the array. And then we will swap the root element in the heap with the last element in the heap and reduce the heap size. This approach lets us sort the array in place, that is O n log n time complexity. By always moving the largest element to its correct position, we sort efficiently without extra memory. Now, let's begin the swap and shrink process. First, we swap 8 and 1 and then reduce the heap size by 1. This means we remove 8 from the heap. Now we need to heapify the tree again. So we swap 1 and 7 and then 1 and 3 to restore the max heap property. Next, we repeat the process. We swap 7 and 2, reduce the heap size by 1 and heapify the tree once again by swapping 2 and 3 or 2 and 6 followed by 2 and 5. And this process continues until the whole array is sorted. The swap, shrink, and heapify steps are the heart of heap sort, and they bring powerful advantages. First, they ensure efficient sorting by always placing the largest remaining element in the correct position with a time complexity of n log n. Second, heap sort works in place, so no extra memory is needed. Unlike merge sort, everything happens within the original array. Third, it offers predictable performance. Even in the worst case, it won't degrade like quicksort and always runs at n log n. And finally, Heapify maintains structure, keeping the data organized after every step and ready for the next move. Together, these steps make heap sort both space efficient and reliable. Now, as we reach the end of the process, lastly, we swap 2 and 1, reduce the heap size one final time, and we are left with one single element. At this point, the heap has been reduced to one element and the array is fully sorted. Now that we have seen how the algorithm works step by step, let's move on to the next screen and look at the actual code implementation. Let's dive into the code, starting with the real workhorse, that is heap function. First, we find the largest element among the root and its children. Here, largest is initially set to the root and then we calculate the left and right children indices of the root. Next, we check if the left child exists and if it's larger than the root. If the left child is within the bounds and larger, so we set largest to the left child. Now we do the same thing with the right child. If the right child exists and is larger than the current largest, we update largest to the right child. If the largest value isn't root, we swap the root with the largest child and call Heapify again to ensure the subtree remains a valid heap. This recursive call ensures that after swapping, the heap property is maintained throughout the tree. Now, let's move on to the heap sort function. We begin by building the max heap. Here, we loop through all non-leaf nodes starting from the bottom and call Heapify to build the heap. After the max heap is built, we move on to sorting the array. We swap the root, which is the largest element, with the last element in the heap, reduce the heap size, and re-heapify the root to maintain the heap property. We repeat this process until the entire array is sorted. Finally, we call the heap sort on an input array and print the sorted array. This sorts the array and outputs the sorted result. So that's how heap sort works in Python, or probably in any language I should say. Building the heap, swapping the elements, and re-heapifying to sort the array. Up next, let's take a look at the time complexity of this algorithm with the graph. Here we see runtime complexity of heap sort. Notice that it has consistent runtime complexity of n log n for best, average, and worst case. This makes it reliable and predictable. In contrast, quicksort has an average case of n log n, but its worst case can degrade to on square due to poor pivot selection. Heap sort, on the other hand, maintains n log n even in the worst case, ensuring more consistent performance. And that concludes our look at heap sort. Thanks a lot for watching, guys. Hope you found this helpful. If you enjoyed this video, make sure to hit the like button and don't forget to subscribe. I'll see you in the next one. Until then, keep learning, keep coding. Thanks again.